Hello everyone, I hope you're doing well. In this video, we'll be doing the most wanted derivation, which is the derivation for the field equation of motion that we know as the Lagrangian equations of motion. And these are extremely important in classical field theory, quantum field theory, and in general. And these equations will be in terms of field phi. And that's why they are called as the field equation of motion, because we will be considering the fields instead of the position and momentum coordinates. This video or this problem is the direct application of the concepts that we have learned before about functional derivatives and how to find out the functional derivatives. Here we'll use those similar concepts, and using those concepts we'll be able to derive the Lagrangian equation of motion. So let's quickly get started and see how we can do that. What I have wrote here is the Lagrangian equation of motion, and we can see there are some indices involved as well. First of all, the starting point is action. So let's define action. We know that the action is defined as S equals to, S is for action, and there is the integral, and we have Lagrangian density, and this Lagrangian density depends upon three things. First is phi, second derivative of phi, which I'm taking as, okay, for simplicity I'm gonna use m, because you can identify it as m better than mu. This was mu symbol like that, but it's really hard to write it here, so I'm gonna use m instead of mu. So it depends upon this thing, and the third dependence is on space variable. And most of the times what people do is to omit the spatial coordinate or spatial dependence, because they consider the translation symmetry, and under translation symmetry the explicit dependence upon x is neglected. They see that, okay, what matters is phi at the end. So yeah. Okay, so we were writing down the definition of action, and then there is this integral over whole space, so we can do it like that. Alright, so we have successfully defined action, and we can see that this is a function. Lagrangian is a function. It depends upon point-wise values of phi, delta m phi, and x. It depends upon the point-wise value. However, action is a functional, and it depends upon the whole field at all the spatial points, not only at just one point, but all of the continuous points wherever it is defined over the whole space. As you can see, it's the integration over the whole space, so it considers the whole space. So action is a functional, however Lagrangian is a function. Alright, so this is a function. Now what we want to do is that we will use the variational principle and the stationary action, the principle of stationary action, and I'm writing it here so that you know what we are doing and why we are doing it. So the principle of the principle of stationary action. Through variational principle, we say that the variation in action, the infinitesimal variation in action, is zero. This is the stationary this is the principle of stationary action, and this principle actually leads to all of the physical trajectories that we see all around us. The projectile motion, why particles follow the projectile motion, why it doesn't follow the other paths, why the light travels in the trajectories we see than the other infinite number of trajectories that it could have taken. So it's the action of, oh sorry, I always mix action and principle. It's the principle of stationary action that derives that guides the particles to follow a certain kind of motion. So yeah, they are the basic, that is the basic principle that leads us to the principle of motion. So we'll see those equation of motion later, but that was something that I wanted to say. Now let's proceed and see what else we will do. We know that I told you in our very first video that the variation in action is actually equals to that integral and differential form that we used everywhere to calculate the functional derivative. That thing is actually equals to the variation of the functional. Okay, so we have discussed that thing in our very first video where we were introducing functionals. So the variation in action is actually equals to this integral form, which is delta s by delta phi. Okay, and it's dependent on x, so we can write of x, you can say, and some test function which could be, let's say, g of x, and you can use z at the end. We can just equate and get what we wanted, and d dx. Okay, that is how we define action, the variation in action, and that should be equals to the differential form as well, that is d by de. And action, the action will be varied by phi plus e g. Okay, we'll do that, and all of it at e equals to 0. Okay, so here action is a functional of phi. Okay, it depends upon the field phi. Also it depends on this thing, but writing alone phi is enough, because the derivative of phi is obvious thing. We can do it if we know the phi thing. So the basic dependence is on phi. Alright, so this is the starting point and this is the ending point as well, we'll see. And that is really important equation that we have written down, that we have written here. So we will start with the differential form. Let's start with the differential form and proceed with it. And d by de. Then we have action at a new argument, which is phi plus e g. We need to calculate it. Okay, that is something that we need to calculate. So for that purpose, let me do the rough work, and in rough work we'll write down what action was. So action at phi was equals to, we have written down it, Lagrangian at phi delta m phi comma, this is comma, sorry, and x, and we have d dx. Okay, we want to have Lagrangian at this new argument phi plus eg, and we will introduce perturbation, small perturbation in it. So let's do that. Phi plus eg, that would be equals to integral, and I'm writing down Lagrangian, and the argument will be written like that. Now you see x will not change because the field is being changed, only phi is changed, so x will stay the same. So x will stay the same. I'll write x first, that doesn't matter. Okay, it's irrelevant wherever you write it. Next, phi will change to phi. It was phi of x, right? So you can write it, or it depends on you. So phi of x plus e g of x, right? Then we will have a comma, just differentiate it, so there is a comma, and then we will have delta m phi. So keep that in mind, that if phi was there, then it was the derivative of this phi field. Okay, now phi has been changed to phi plus Eg, hence it will be a derivative of this whole thing. So derivative of phi plus E is a constant, so it will come outside, and derivative of G, it's M. Okay, so we'll write delta M phi plus E delta M G, G of X, you can write that, and bracket closes, and we have D dx. This is the new functional that we need to insert here. Okay, and we'll do the simplification from that point on. So okay, I hope the point is clear to you people. Alright, so the next step is to find out the d by de of this thing, and simultaneously or at the end we can put equals to 0. So let's see how we can do that thing. So we have d by de. Oh, it's really thin. D by d. Now the new s, which is integral d dx, and we have that lengthy Lagrangian, and this Lagrangian is x stays the same. Then we have delta m, oh sorry, phi plus Eg. Okay, delta m phi, and it's x, you know, phi of x, keep that in mind. Eg of x, m, that's m. Okay, bracket closes. So that is what we have, and it is at e equals to 0. Now we need to find out d by de. Now you know that d by de and that integral, they are independent of each other, so we can just move that integral inside, or sorry, that derivative inside, and we can apply the derivative directly inside. So it's gonna become like that, d dx, and there is d by de of this whole Lagrangian. Okay, d by de will only apply on the terms that contains e, and only Lagrangian contains e. So now we'll use the chain rule, because we can see there is inside indirect dependence upon e. So we have three different parameters. One is this, second is this, and third is this. Only these two depend upon e, so only these two arguments will be affected by this derivative. This will stay the same. Okay, it will not be affected. Now let's use chain rule, and we'll use chain rule right now. And what we do in chain rule is that we will have this structure, partial L, there will be partial derivative of L with respect to one of the dependencies, which is this. Okay, first dependency, I'll write it as d1, first dependency, dot the derivative of this dependency with respect to de, with respect to e. Okay, that is the rule that we will follow, plus the partial derivative of Lagrangian with respect to second dependency that contains e, because we are actually doing it for d by de of Lagrangian. So which is this is d2, the second dependency, and the derivative of second dependency with respect to e. That is the rule that we will be following. Okay, and in this, based upon this rule, we'll write down everything. So let's do that. It's partial L by partial d1. Let's put the value of d1, which is phi plus Eg. And here in L it contains all these things. Okay, so I'm not gonna write x because it's just not necessary. You can write it. I'm just for simplicity I'm not writing it because there is no application of x here. So this is Lagrangian with its dependency dot the second term, which is d by de of d1. What is d1? Phi plus eg. Alright, then there is a plus sign and there comes the second term, and it will be partial L with this long dependency. You'll write down this long dependency. Okay, this is your job. And partial L by partial of d2. What is d2? d2 is this whole thing. So let's write down this whole thing. Partial m phi plus e partial m g of x. You can write that. Alright, and dot we have d2 d2 by de. Okay, we'll do that thing. Let's make some space. Yes. Okay, and we will write down the second term, which will be d by de of d2. d2 is this partial m phi plus e partial m g of x. Alright, the bracket closes, this big bracket closes, and everything at e equals to 0. So here e equals to 0. Now there is a quick simplification that we can do right away by putting e equal to 0 wherever we can do that. So here we can put e equals to 0 because there will be no change. So e equals to 0, this term vanishes. E equals to 0, this term vanishes, and this term vanishes as well, this whole term. So in simplification we can write d dx, and we have partial L, and there is now normal dependence phi partial m phi and x. Okay, there is no e here now, and by partial phi because this e was vanished. Dot, here we cannot put e equals to 0 directly because there is a derivative with respect to e, direct derivative. Let's find out derivative first and then we can put e equals to 0. So derivative will be applied on phi. It doesn't contain any e, so it will become 0, that is 0, plus this g comes outside and there will be derivative on e, de by de, which is 1, so only g survives, so it's g of x that comes outside. There is no e involved in here, hence putting e equals to 0 doesn't make any difference. Plus now here partial L by partial this whole thing, so you will put e equals to 0, this term vanishes, and also in dependency there will be normal dependency left, as was the case with this one. So I'm gonna write it here. There will be partial L, normal dependency, which is phi partial m phi and x, okay, by partial m phi. You can see here this term vanishes, so only partial into partial m phi left. Then we will find out derivative here. The derivative of this term becomes 0 because there is no e here. Here partial mg will come outside and there will be de by de, which is equals to 1, hence partial mg survives. So here we have partial mg, g of x. G of x. Alright, so this is the simplified form so far. We'll close the bracket. Let me rewrite it in next page. Okay, so inside this bracket we have L, which is simplified, so I don't need to write down its argument anymore because we know what kind of argument it has. So partial L by partial phi g of x plus partial L by partial m phi, and then we have partial m g of x, bracket closes. So this is the simplification so far, and now what we are gonna use is that we are gonna use this property for this g of x arbitrary field, that it vanishes at the boundary, and for all those fields that vanishes at the boundary, they satisfy this condition that the derivative of this field and with that it's equals to 0 if it satisfies the boundary condition. So under that condition we get, if we apply the product rule on it, so it's like this thing while this intact. I'm applying just boundary condition, the product rule, so that we can get an expression for this term, so that we can just replace it. So first this term as it is and the derivative of g of x. Now g of x as it is and derivative, which is partial m of this thing, which is partial L by partial m phi, and that whole thing to be equals to 0. This kind of simplification is really common when you do problems like these. We already had encountered such similar kind of problem before. We have already done that, and it happens many a times, and it's really common in classical field theory, so get used to it. So here we have this term over there, so if we want to find out value of this quantity, what we will do is to take this quantity to the other side of the equation, so it will become negative to the other side. So let's do that. Okay, we can just simply take it to the other side and say that it is actually equals to negative of this quantity. Okay, so what this step has done is that it took g of x out of the partial derivative, and in that way we can just factor out g of x. This was really important, we'll see why. So now we can put this thing here in this expression and we can simplify. Let's do that. Give me a sec. Okay, we know what it equals to, so yeah. Okay, so that is equals to ddx and partial Lagrangian density g of x minus, it will be minus now, so there is this derivative on partial L by partial m phi. Okay, and g of x, the position of g of x doesn't matter, but because we know that it is outside of this partial derivative. Once this thing is clarified, there is no need, the position of g of x is irrelevant in that case then. So now we can factor out g of x from this expression, and we can write it here, maybe, yeah, that's fine. We can write it outside, and inside we have partial L by partial phi minus partial m of partial L by partial m phi, and bracket closes. And now you can see that we have simplified it so far. We can put that equals to that integral form that we had in the really start of the video. We mentioned that at the really start of the video, so we can do that. Let me do this thing. Okay, so what we can do is put it equals to, I'm just deciding between the colors, pardon. Okay, so we can see that that was equals to the variation in action, which was in turn equals to that integral partial s by partial phi g of x and d dx. So if you do the comparison, you will see that this is g of x, this is g of x, d dx integral. So this inner term is actually the functional derivative of action with respect to phi field. So we can put it equals to this thing. So now you know that what does the functional derivative of action equals to. Okay, this is equals to this. However, there is one thing still missing, that is the principle of stationary action. Let's do that here. So we'll mention here that enforcing the principle or using the principle of stationary action, we get that the variation in action should be equals to 0. If the variation in action is equals to 0, it means that this integral which it equals to should also be equals to 0. And we know that g of x is a arbitrary test field, so it couldn't be 0. We cannot specify it because it's arbitrary. Hence, this quantity should equals to 0. Okay, so there is something that is making this integral equals to 0. So it could be either g of x or this thing, g of x, since it's arbitrary, and you cannot assign something to arbitrary things. So if g of x couldn't be 0, then this thing has to be 0, and this thing, as we have seen above, this thing is actually equals to partial L by partial phi minus partial m partial L by partial m phi, and that should be equals to 0. And this is, everyone, the most wanted equation of motion that we needed. So this is the Lagrangian field equation of motion, because it involves fields, phi field, and okay, yeah, that's, and L is the Lagrangian density, S is action. That doesn't appear directly in here because we are now seeing this equation that contains Lagrangian, that contains phi, and that contains you can see these partial derivatives, and the index is m here, and the index is also m here, so there are similar indices also above and below in partial derivatives. And yeah, that is it. We have successfully derived the Lagrangian field equation of motion, and in next video we'll see that how we can use this equation, this a basic setup to derive equation of motion for different fields. It will be for scalar field, fermionic field, bosonic field. We'll see that how we can employ this equation to find out the equation of motion for different kinds of fields. Okay, and then we'll study those particles and everything related to that. So we have successfully established some ground for the further work, and in next video I'll meet you with a scalar field and we'll derive the Klein-Gordon equation. Take care and goodbye.